Hello class, today we're going to be talking about the properties and proving the properties of a perpendicular bisector. So if I have a line segment and I want to create a perpendicular bisector, I'm going to use GeoGebra to make the perpendicular bisector because first of all, every bisector has to go through the midpoint. So I'm going to actually find the midpoint of the line segment. And I know it's the midpoint because it's the same distance from A as it is to B. And if you want to confirm that, here you have the distances between the two. And no matter how I change the endpoints and the location of the endpoints, I will still have C is the midpoint of A and B. And I'm going to actually rename it instead of C. Let me rename it M to let you know that's the midpoint. And as you know, the perpendicular bisector has to go through the midpoint as well as being perpendicular to the actual line segment. So I'm going to actually now create a perpendicular line segment. A perpendicular line to the line segment. And as you can see, that no matter how I move the corners of the point, M is still the midpoint, and the line that I drew is a perpendicular bisector because it makes a 90-degree angle. So let's just put a point on this perpendicular bisector, and we're going to call this point C, okay? And let's see how C compares to A and B. Let's draw line segments between A and C and B and C. In other words, let's draw line segments from the point on the bisector to the endpoints. So what do we notice about the two triangles that are produced when we do that? Well, let's take a look. First of all, we know that since CM is a perpendicular bisector of AB, that AM is congruent to BM by definition of perpendicular bisector, and that the measure of angle AMC is equal to 90 degrees and the measure of BMC is equal to 90 degrees. So therefore AMC is congruent to angle BMC. And then we also know that CM is congruent to itself because it's the same line segment. So we can show that this triangle is congruent to this triangle by side, angle, side. And since these two triangles are congruent, then that means that a component corresponding parts of congruent triangles are congruent, which means AC is congruent to BC. And therefore we have proven what's called the perpendicular bisector theorem. And that means for any point C on the perpendicular bisector, as long as it's not on the line segment, any point C that is on the perpendicular bisector is going to have that same property, that it's going to be equidistant from the endpoints of the line segment because it's always going to form two congruent triangles. So now let's take a look at the converse of the perpendicular bisector theorem. Let's say I have two endpoints A and C and a point C such that it's equidistant from A and B, which means it's the same distance, okay? Doesn't matter where. And let's see what happens. How can we prove that C is on the perpendicular bisector? Well, first let's take a look at the midpoint of the line segment, and then let's form a connection, a line segment between the midpoint and C. Oops. As we can see, we have two triangles. Well, what do we know about the triangles? Well, we know several things. First of all, we know that oops, wrong one. We know that AC is congruent to BC, that's given. And we said that since M is the midpoint, then that means that AM is congruent to BM by definition of midpoint. And we know that CM is congruent to CM because it's the same line segment. So we've shown that we have three pairs of corresponding sides that are congruent. So we show that triangle AMC is congruent to triangle BMC by side, 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 which means that that angle AMC is congruent to angle BMC by CPCTC. And to prove that it is a perpendicular angle is that we have to show that there is no distance that is going to be shorter from C to the line than it is from C to M. So no matter how close I put C, I'm always going to have the shortest distance. So this has to be a perpendicular angle. So therefore, that's the converse of the perpendicular bisector theorem, that C would have to be on the perpendicular bisector in order for this to be true. So notes on page 81, says the perpendicular bisector theorem, and it says that if a point is on the perpendicular bisector of a segment, then we know that it is equidistant from the endpoints of the segment. So in this case, CA is going to be equal to CB because C is equidistant from A and B. And then the converse of the perpendicular bisector says, if I have a point that's equidistant from the endpoints on the segment, such as what D is, then it is on the perpendicular bisector of the segment, which means since DA is equal to DB, then D lies on the perpendicular bisector. So now let's take a look at the angle bisector theorem. In the angle bisector theorem, we have just a random angle, and as you can see here is to measure the angle. It can be acute, obtuse, and even right, but it doesn't matter. We're just going to start with just a random angle BAC, and then we're going to construct the bisector of the angle, and the GeoGebra will do it for us. So here is the angle bisector, and we're going to place a point, just a random point, anywhere on the angle bisector, as we can see here, as long as it's on the interior of the angle and not on the exterior. And as you can see, line AD is array AD is an angle bisector because it breaks the angle into two congruent pieces. But let's take a look at the relationship between the point D, the random point on the angle bisector. If I want to measure the distance from the point D to any line, I would have to find the perpendicular distance. So what we're going to do is we're going to make a perpendicular line segment that goes through D and is perpendicular to this side of the angle, and we're going to make another line segment that's perpendicular to this side of the angle, and it goes through D as well. So as you can see, we actually have now two triangles here. We have a triangle with the black side of the angle, the red angle bisector, and the blue perpendicular line segment, and we have another triangle with the black other side of the triangle, the red angle bisector, and the green perpendicular line segment. And let's see, what's the relationship between these two triangles? Well, of course, we can see that they are congruent. And anybody want to take a guess at how we know they're congruent? Well, we know that this side is congruent to itself. We know that these two angles are congruent because they're both 90-degree angles, and we know that these two angles are congruent because of the angle bisector. So if you said they're congruent by angle, side, you're absolutely correct. So since these two triangles are congruent by angle, side, then we can say that DE would have to be congruent to DF by CPCTC, which means that any point D on the angle bisector is going to create two congruent triangles, and therefore that point is going to be the same distance from each side of the angle, which means that D is equidistant from any side of the angle. But this only works if we know that AD is the angle bisector of angle A. What if we do not know that AD is the angle bisector of angle A? And let's switch it around. What if we just know that DE is congruent to DF? So let's start off with the fact that let D be a point, and it doesn't have to necessarily be on the angle bisector, but let D be a point such that D to one side of the angle is the same distance from D to the other side. In other words, D is equidistant from the two sides of the angle. Well, and let A connect with D just in a line segment. And so we want to take a look and see, what do we know occurs? Well, since we can see, since we can see that DE is congruent to DF, and we also know that because from the definition of point line distance, that this is a perpendicular line, then that means this angle is 90 degrees and this angle is 90 degrees. And since AD is the same line segment, then that means that we can show that triangle ADE is congruent to triangle DAE is congruent to triangle DAF by the hypotenuse leg theorem, because we have two right angles, we have hypotenuses that are congruent, and we have two corresponding legs that are congruent. So therefore, triangle DAE is congruent to DAF, and then since that's the case, then we know that angle DAE is congruent to angle, DAE is congruent to angle DAF by CPCTC. So we've also proven what's called the converse of the angle bisector theorem. And those notes are found on page 83.